that's a fancy word for basically the following. Previously we had S1 is equal to alpha S0. And now we're going to allow that not to be true. Now we're going to say I'm going to have signals that are not linear, that are not scalar multiples of each other. What that lets you do is, so in binary, it actually doesn't make any sense to allow that. It's not optimal to go into, or to allow these signals to be linearly independent. But what it does allow you to do is something like this. You can have S0, S1, S2, and S3, and so on. And these signals are now not linearly independent. And that actually turns out to be more efficient. That's a better way to do things. Now, I mean, all along we've been talking about binary, but let's say we had this kind of system. 0, 1, 2, 3. If I'm talking about binary data communication, how could I possibly use this? Any ideas?
Send 2 bits.
Send 2 bits at the same time. So here I would send 0, 0, 0, 1, 1, 0, 1, 1, like that. And in fact, there's no limit on what you could do here. So what we will find is that because these are now multi-dimensional signals, they sort of exist in what's called a constellation. And the largest constellations that are used in practice can have 6,428 points. So they can be actually quite large. But the fundamental idea is that now these signals are not linearly dependent, or they're not simple scalar multiples of each other. They're sort of spread out in what we will call signal space. So where this is going to go is that if you think way back to linear algebra, so I think everybody here took a first-year linear algebra course, you will probably remember the term vector space. So signal space is just a vector space with signals. So in other words, each of these signals, we can represent it equally well as a vector. So remember, these are supported, these have support from 1 to NB. So basically it's just a list of NB real numbers. So that can be represented as a discrete function like this, or it can also be represented as a vector. So in other words, all of these vectors will exist in a vector space with all that implies. So a vector space has a basis. The basis is sort of the fundamental vectors in which they can all be expressed. And what we're going to find is that what you have to do is you have to match filters. The matched filter, you now don't have one matched filter, you have multiple matched filters, and basically you have one matched filter per basis vector. And that will express sort of where in signal space each of these signals exists. But since I'm willing to bet that nobody remembers anything about vector spaces, let's start there. Okay. The idea is that signals S0K and S1K can be expressed either as discrete time functions or as vectors, as 1y and b vectors. So in other words, I can write S0 vector. In my notes, I use boldface letters for vectors, but since it's hard to write boldface on the board, I'll use the little arrow to designate a vector. S0 would be S01, S02, and so on, up to S0NB. And S1 vector is is that now S1 vector is not, in general, a scalar multiple of S0. So I said this word a second ago, but what's the technical term when this is true? Does anybody know? It's linearly independent. Or more generally, if I have a whole bunch of vectors over here, I want to represent, and I can't represent an additional vector in terms of a linear combination of the vectors on the right, then those vectors are linearly independent. Okay, so we need a few concepts from vectors. Okay, vector dot product. So let's let A and B are 1 by n vectors. Then A dot B is equal to the sum from I equals 1 to n of AI BI. Dot B is equal to what? It's 1 times 2, which is 2, plus 1 times 0, which is 0. Which is 2. If the dot product is 0, if A dot B equals 0, then there's a special term for A and B, that A and B are what? Anybody remember? They're perpendicular. I prefer the term orthogonal. But perpendicular will work too. So that basically means 90-degree angle between A and B. And in particular, there's an idea in the dot product of projection. So for instance, if A and B look like this, then A dot B, in some sense, this is not completely accurate, but in some sense, A dot B gives you this projection. If you project A onto it like that.
It's not A B cos theta.
What it technically is norm A, norm B, cos theta. So this theta, yeah, it would be, if B were unit norm, then this would be exactly the projection onto the B axis. In fact, that leads me to the second thing we need. So we have vector dot product.